10.3 Introduction. In this chapter, we're going to start off by talking about what a polar curve is, and then talk about how to integrate and differentiate polar curves. So first, let's go ahead and just give out some definitions of what a polar curve is and how to analyze it. So a polar equation enables us to define some interesting curves that would be difficult or impossible to define if we were in the form y equals f of x. In polar coordinates, we define the origin as O as the pole and the positive x-axis as the initial ray of angles measured in the usual trigonometric way. So in polar coordinates, we define the x-axis as usually our starting point, and then we're going to use the pole, which would be the line, as our radius, which I'll talk about in a little bit. Each point, P, is defined as r comma theta. So instead of x and y, we use r and theta, where r is the distance from the origin, and theta is the angle that you're revolving. Where r is directed distance from the origin, O to P, and theta gives the directed angle from the initial ray to the ray. So the first thing I want you to do is go ahead and draw these two things into your notes. We're going to go ahead and take a look at this in a second, but I want you to draw these two things so you can follow along in the computer model I'm about to show you. So if we look here, we have the coordinate 2, 2, right? So this is the coordinate 2, 2. And the way that we get this coordinate is we go 2 to the right and we go 2 up. So the first thing we do is we go 2 to the right and then we go 2 up. And that was our Cartesian way or rectangular way of finding coordinates. It would be the x and the y value. When we talk about polar coordinates, a little bit different. So I'm going to leave this point A and I'm going to switch from rectangular coordinates to polar coordinates. So a polar graph looks something like this, where we have these rings and angles. Realistically, when you draw it on your paper, it's going to be blank like this, but I'm just putting this background so we can kind of see what's going on. And what's going to happen is I'm going to put a point on the graph. So B, I'll put this point on the graph right here. And the reason it starts out right here is it tells me that theta is 0. So I'm 0 degrees from the x-axis. And B is 2. So that's the distance from here to here. So the distance from the origin to my point. And when I rotate it, you can see that B moves with theta. So as I go ahead and increase theta, we can see how that will change how far it's revolved around the x-axis. Notice the distance here doesn't change. Only the angle changes. So the theta component talks about how far you're revolving from the x-axis, and the B value, you can think of it as r, is our radius. So as I push this thing out, it just becomes further out. So as r changes, it literally just shoots out from the origin. And if I go negative, watch what happens. When B becomes large, it's going to shoot out from the origin. And when B becomes negative, it's actually going to go in the opposite direction. So notice, this still has an angle of 36 degrees, but then it goes backwards. Okay, so that's another component, is that it can go backwards. So that brings me to my next point, is that if I had theta, which is equal, I'm going to make it 30 degrees, just so we can use a common angle here. And I say B is equal to negative 2.5. This would be the same as me finding the whole angle, so 210. If I make theta equal to 210, and then I make B 2.5, I get the exact same coordinate. So radians coordinates and polar units can have the same place on the graph with different coordinates. Okay, so now let's talk about how to get this value of 2, 2. So now let's talk about how to get the r value if I want to convert this to polar units. The first thing I need to do is go ahead and make a triangle. So what I'm going to do is, now that I have a triangle, I can use the Pythagorean theorem to find this side. So I know that this length is 2 and this length is 2. So then use the Pythagorean theorem and you get that the radius, or r, is 2 square root of 2. And I know it's going to be a 45, 45, 90 because it's an isosceles triangle. So then this angle is going to be 45 degrees. And so now I get that this is the hypotenuse of that triangle. And so I get that theta is 45 and this is 2 radical 2. So the coordinates here would be this coordinate here. 2.83 comma 45 degrees, or pi over 4 radians. So that's kind of how polar units work. The first value of a polar unit gives you the length, and the second value gives you the angle. So polar units work in length and angles. So now just to go ahead and write it in the notes, if you want to write it down, we would have here that this distance here is r, and this value here, this angle, is theta. And the way we do it is we draw a little triangle real quick. This is 2, this is 2. So then Pythagorean theorem, this has to be 2 radical 2. So r is 2 radical 2, and then our theta value was pi over 4. So then the coordinate of A would be 2 radical 2 comma pi over 4. This is equal, this is the same exact point as that one. Alright, now let's talk about how polar coordinates are not unique. I did show a quick example about this, but just to formalize it, this point right here is going to be 2 radical 2 comma pi over 4. And then this point down here is going to be 2 radical 2 comma 5 pi over 4. Now, if I were to go the opposite direction, if I go this way, this point is also 2 radical 2 comma negative 3 pi over 4. And I could also call this point here negative 2 radical 2 comma 5 pi over 4. Because I go 5 pi over 4 degrees and then I go backwards. So there's lots of different ways that you can get the same point on a polar grid using different coordinates.